Hello, Internet. So I was reading the Groovy documentation. I'm not sure if you're familiar with Groovy. Groovy is a interpreted language. It's based on the JVM, so it's interoperable with Java and Kotlin, as well as a few other of the JVM language. I think Scala. But the cool thing is it's an interpreted language, so you could do a lot of things you probably shouldn't do. But it makes it really handy. So one of the cool things that I was reading about is there's a memoization feature, not memorization, memoization. It's a weird spelling, and what that means is it's a cache. And so let's say you're doing a function that calculates some value. Given a set of inputs, you get something back out. Fibonacci is a good example. When you're calculating that, there's a lot of time, especially in a recursive function, when you're going to need the previous value. In that case, if you're doing a recursive thing, you're going to potentially need that recursive or that value multiple times. So if you're talking about Fibonacci, you'll need f of 1, however big your number is. So if you're calculating the Fibonacci sequence for, say, 13, you're going to calculate f of 1 13 times, which scales poorly. So memoization is basically the idea that you can cache that constant value, and you can effectively say f of 1 is equal to this value, in this case 1. And so that way, you're just referencing that value once. You'll calculate it once, store it in a cache, and then any other time you need to actually reference it, you won't go and calculate it in the function. You'll just look it up in the cache, which is really handy. Not so much when you're doing f of 1 because you're already at like the bottom of the recursion. But if you're doing like f of 100, that is a huge amount of things you don't need to recalculate. And so what I was reading about is Groovy has a feature that allows you to effectively tag a function as a memoized function, which behind the scenes will actually cache it for you, which means you don't need to implement the cache. It should just do it for you. Never used the feature, but I kind of want to try it out, and so I figured I'd do it live. That's either going to be great or it's going to go horribly wrong. So I used Fibonacci as an example, and that's what we're going to be doing. So we need something that will calculate Fibonacci, and we're going to do a recursive algorithm to calculate Fibonacci. So the way that works is you're going to have some sort of int, that's your return, and you are going to do a fib of some function. So int n, sure. And so the general idea of Fibonacci is f of the function or the result, f of n, we'll just write it this way, is going to be equal to f of n minus 1 plus f of n minus 2. That's Fibonacci. Now there's two values that need to be defined. F of 0 is equal to 0, and f of 1 is equal to 1. There's also a value of f of 2 equal to 1, but that's strictly because a 0 plus 1 is 1. So nothing crazy there. Some definitions of Fibonacci don't include this 0. I'm not really sure which is the correct version, but I've included it just because I want to. And so what we need to do is if we get 0 or 1, we need to return that value. Otherwise, we need to do this function. So we can either do an if or a switch or something like that. I think a switch makes sense. I'm not really sure if that's a good idea, but why not? So for case 0, we're just going to return 0. You don't actually, in Groovy, you don't necessarily need to type a return. It will return the last line in your function if you don't have one. There's a lot of things in Groovy that make it really easy to write code, but are also really easy to kind of trip you up. So if you've never used it before, it can be a little bit interesting. It kind of reminds me of JavaScript in that way, where there's certain features that if you can write without knowing about them, and your code will usually work until it doesn't. Groovy has some of those. There's a lot of really cool things. You can do function overrides and things like that. And you'll notice there's no semicolons because it just new lines do that for you. So 0 and 1, we've predefined those as those cases. And then we'll do default, which should catch everything else. Unless you give it a negative number, and then we're screwed. So let's actually, well, if I do that, then that kind of defeats the entire point of doing a switch, doesn't it? We should probably account for negatives. So if n is less than 0, we'll just return 0. Hadn't really anticipated accounting for negatives when I started doing this switch. Thinking about it, we probably don't. It's not really that big of an advantage. It's almost more complicated because now we've got more complexity in our function. But we're going to stick with it because why not? And so assuming we didn't get 0 or 1 and our value is greater than 0 because this will catch everything else, then we want to return the Fibonacci sequence of n minus 1 plus the Fibonacci sequence of n minus 2. The order of this doesn't really matter because, again, we're hoping to memoize these things, so it shouldn't really matter, because ideally, if we're doing this right, we'll only calculate each value once, regardless of what we're using. So we can delete our notes, and that should be our entire function. I'm going to run this without any other stuff. So I'm not going to add this memoization. We're just going to be able to see how slow this is. So I think the best way to do that is to kind of, let's throw some timing in there. So yeah, how do we want to do this? We're going to have an int iterations, and this is just going to be a sort of a constant. We're going to set this to say 20. Why not? And then for int I equals 0, while I is less than the iterations. So we're going to repeat however many times. And then I want to just calculate fib of, let's say, 100. That might be kind of big. Sure, why not? I want it to be big enough so we kind of get that exponential scaling, because this function is not going to scale very well. But I don't want it to make it too long because we're doing a lot of these calculations, and that would just make you wait. So calculation of the Fibonacci sequence of 100, we're just kind of discarding the result. Let's print it out like so. Sure. Thinking way too hard on how I want to format this text because I hadn't considered that. So we're just going to put commas between everything, and so it will just print on the same line until we get to the end. Do I want to do that? It's just going to print the same thing over and over again. Let's just do print line. That makes way more sense. So we're only printing the final result. We're calculating the Fibonacci at 100. And so that's going to get us some value. I don't actually know what value. For this example, it actually doesn't really matter if this algorithm is correct. It just matters that we have recursion. Probably not the best way to say that. It kind of is a get out of jail free if my stuff is wrong. But that's sort of the idea, is we're worried more about caching this and how to use that than we are to implement this. So that should be good. The only other thing I want to do is track our time. So we have a function that's going to run. We could do like a local date time and get like the now. That would get like the current time in where we are. The problem with using like local date time, and this is beyond just Java stuff, when you use these functions, they're not necessarily designed for like low-level system tests. They're not going to get clock times. They're going to look at wall clock times, which is like if you look at like the clock in your car. That's the kind of clock they're worried about. They're not worried about this much time has elapsed since whatever. That's not necessarily the idea there. You can use it that way, but it won't be as accurate. So there's a system.nanotime, which is designed for these kind of uses, and that's what we're going to be using. So long nanotime. Let's just call it start time. That makes way more sense. Start time equals that. Long start time or end time equals the nanotime at the end. And then we can just subtract those two. Difference time, because why not? And we'll just do end time minus the start time. And that's going to get us some value in nanoseconds that it took to actually run this. So system.out.println. We'll probably want to convert that into something that isn't nanoseconds, because I have no idea what a nanosecond is. Like, I get the idea, but I don't. If I just give you a number in nanoseconds, I don't know, is that big? Is that small? What does that mean? So we'll probably want to convert that into either seconds or milliseconds or something like that. Something that's a little bit more tangible. So we'll do that in just a sec, because I don't actually know the conversion. But we'll just write time taken. And the cool thing is Groovy has its own strings. So when you do double quotes, those aren't Java strings. They're actually Groovy strings, which means you can do something like this and just insert your own variables back into your string. You can't do that if you use Java strings, which you would do with single quotes. Those aren't characters anymore, like if you use Java or C#. Those are Java strings. It's a little bit different. A few other quirks, if you just use like the normal like array creation, this creates a list, an empty list. It does not create an empty array, and they're different. So it's just Groovy prefers lists over arrays, which Java is the opposite. So again, you kind of have to figure that out. But anyway, this is our difference time. I should be able to just run this, and we should get a number out. And then we can kind of refine the time so it means something. And then we'll actually refine this, and just theoretically, we should just need to stick an @memoized on it, and it should work. So one of the quirks of Groovy, I have completely screwed up and named my function wrong. And I don't know how. Let's see here. No signature. Oh, this isn't a static function. And since it wasn't static, we were trying to reference it from a static context. No idea what that is. So that was totally broken. We fixed it now. But you'll notice we didn't get a compile error. This isn't a compile error here. It looks like a compile error if you were using Java or something. This occurred at runtime. And that can be good and it can be bad. The problem with this is if you don't have like good tests, or if this code path isn't always traveled, your code may not actually work at that point, and you wouldn't know it until you actually got to that point. So there's not necessarily, it gets weird. I guess that's the best way to put it. There is a way to, I think it's called static compile. There's a way to actually compile things, and that will force everything to statically compile, which will actually get you compile time errors. That isn't the default. So you kind of have to be concerned or look into that. So I think we fixed it. Let's try rerunning that. And hopefully we get something that's a little bit more helpful than an error. Looks like it's taken a while. That's good, I guess. Don't know entirely how long this is going to take. Probably a very long time, because we're doing 100 times plus 99. Effectively, this is a factorial issue. So we're doing 100 factorial iterations 20 times. That's not great. So I may actually want to stop this because that's going to go for a while. Let's move this down to like 40. That's still probably going to take quite a while. This is sort of one of the classic examples of how to write really bad code and then how to make it good or better. I won't necessarily call this switch good. It seemed like a good idea at the time, and then it didn't really work out. But this is sort of the time complexity issue. It's big O notation or just time complexity. And so it's sort of a measure of the complexity of an application. It doesn't really look at, oh, this function takes, I don't know, 30 seconds to run. It doesn't really look at that. It looks more at how much iterations do you have to do. If you apply your algorithm to a big data set, how does that algorithm scale? That's sort of what it looks at. And so there's a bunch of different ways. Big O notation is sort of the most common one that I'm familiar with. I have no idea what that means. We got something there. So big O notation is sort of a measurement of the function complexity. So let's say you have just a for loop and you wanna find an element in a list. The time complexity for finding that element in a list, assuming you just do it naively and iterate over every element, is going to be worst case O of n. And in this case, n is the number of elements in whatever your data set is. Because the worst case could be the element at the end of your list, so you iterate over and check every single element and then get to the end. There's better ways to do that. There's a whole bunch of different searches that you can do to find something better, and those will have a time complexity that is lower than O of n, usually a logarithm of n, because you're sort of dividing the function in half. If you're curious about that, go look up like binary search or any of the other searching algorithms. But I'll kind of leave that here. This is going to take a very long time because it is only printing out 2 of the 20 iterations so far. So we're going to be here all day. I'm going to stop this again. Let's tune that down to 20. I just want this to kind of iterate through and get it done. There we go. That's much faster. So you kind of see, it takes a long time. Let's go back up to 40. The reason we're going to do this is because it doesn't really complete. That's good for us because it means that if I stick at memoized in front of it, theoretically, I don't need to do anything else. I have no idea. I've never used this before. So this is either going to work or I'm going to cut the video and go and figure out how to make it work. But theoretically, this should complete pretty quickly now because all we're going to do is calculate the first 40 elements and cache them. And then every time we need to look this up, we'll get it. So we'll do the calculation once, and then we'll already have stored what the Fibonacci of 40 is. And so the next time we ask for it, it's constant. We just say, oh, that. So it should be quick, I'm hoping. So if I run this, we'll compile it, and we're done. So that is the advantage of memoization. It took no time. This is, I think, there's 9, it goes -9 for nanoseconds. So this would be like 60 milliseconds or something like that. I'm just doing that off the top of my head. I can actually get that conversion 1 sec. I will go and look up how to convert this, which is our nanotime difference, into a millisecond difference, which we should be able to use to actually get a little bit better idea of how long this is taking, and then we can kind of compare them a little bit. So 1 sec. So I've implemented a time unit. I haven't implemented this actually, if it's just a Java thing. So time unit gives you a whole set of different time units. In this case, we're using milliseconds because that's what we want to get to. And so I'm saying for a time unit milliseconds, I want to convert from something else. In this case, we're converting our end time minus our start time from nanoseconds into milliseconds. So this should take all of that and convert it into a millisecond. So we should see 64 milliseconds. So I was pretty close. So that's good. Let's drop this back down to say 30. And we should see sort of a difference here. If I run this with memoized, it's going to take probably about, 62 seconds, because this actual calculation is pretty quick. The slow part of calculating Fibonacci is the iteration, the recursive calculation of this. And so when we take that out, reducing or increasing the number doesn't really matter that much. So if I remove this memoize though, it's a different story. This, I think with 30, we should be able to complete it. Yeah, there we go. But this is still, you can see this is taking a long time. It's the same number of iterations. We're calculating the same thing, but it took 7 1/4 seconds compared to 64 milliseconds. It's almost, I don't know. What is 7,000 calc? So 7266 divided by 62. It's like 100 times slower. And that's going to get exponentially worse. Because actually, it's going to get worse than exponentially worse, because it's a factorial, and factorial grows way faster than an exponential thing. So yeah, it doesn't scale if you're just doing this recursively. But you can just stick this on there and it works. If you're using Java, this memoize thing isn't going to exist. It's not a feature of the language, which this is in this case. But you can just use like a basic array and just store the values in there. And then just before doing all of this calculation, just see if it's in the array. And if it is, then just return that. Otherwise, just calculate it and stick it in the array and then return it. So that's sort of the difference here, is you just need to kind of figure out how to do that. Groovy just gives you a way to do it. And apparently it's super easy to use, because I did it without really knowing what I was doing. So I'll leave it here because I'm kind of going off on tangents. If you guys are curious about more like time complexity stuff, Wikipedia actually does have a decent article on it. It can be a little bit dense, but kind of think of it as looking at how things scale. How, as you increase data, or the size of your data, how things change. So if your algorithm scales, say, n squared, that means every single time it gets exponentially worse. So the first, if you just calculate it for one thing, it just takes an equal amount of time as if it was going linearly. And then the next time it's going to take 2, same thing. But then when you have n equals 3, suddenly it's taking 4 instead of 3. And so that just kind of goes up into infinity. That's kind of the idea. If it's confusing or you think I should spend more time on it, let me know in the comments and I definitely will. I'm going to post this code out on GitHub just as like a little gist, so you guys can kind of check it out. It's pretty easy to get started. I started from scratch 30 minutes ago. So yeah, I'll leave it here and see you guys in the next video. So till then, see you, internet.